So it turns out we're not quite done with the sample standard deviation. There's two possible formulas you might use. The one we had before had to do with deviations from the mean, and then squaring them and summing them and dividing by n minus 1 and then taking the square root. That has a lot of conceptual information in it. You can see you're taking how far away values are away from the mean. So if they're further away, you get larger numbers. And then you're squaring it to make all those numbers positive. They're combining these positive numbers together. If the values are far away from the mean, you get a large answer. And you take the square root, it stays large. So large answers for S mean more spread out data. So it lets you think about what you're doing, but it turns out to be hard to compute those kinds of things with pencil and paper, or back in the old days with adding machines. It was difficult to do it. Now it doesn't really matter what formula you use. The calculator can handle either kinds of formula, and the kinds of things we worry about these days with formulas is whether the kinds of mistakes calculators make with round off, how those errors get compounded in formulas, and analyze what formulas are considered most stable for calculations. People study that for a living. It's called numerical analysis. This formula we have here comes from the days when people added columns of numbers to compute things. So we see in here columns being added. Here's a sum of x's. That's a column of x's. Here's a sum of x's squared being added. So maybe we should imitate what they used to do in the old days. Oh, let's do that. So we make kind of a table. I don't know how much space I need. We'll just see. I need space for 5 things. Okay, so we're starting off okay. So here are the values: -2, 12, 4, 21, -15. And down here we'll put the sums. So we said last time we summed those, we got 20. Because to get the mean, we divided by 5 and got 4. And then that's this. So that quantity in there is 20. This thing here is 5. We're going to square it. So we'll get 400. We're going to divide it by 5. That's 80. So that's what's going to go in there. And the other thing we need is the sum of the squares. So now we'll square these. So this is xi, and this is xi squared, say like that. 4, 144, 16, 441, 225, like that. Okay. Now we need to sum those. So some things I might double check here. Make sure that 21 squared is 441. I think everything should be fine. Okay, clear this. 4 plus 144 plus 16 plus, looking at it, 441 plus 225. Put a minus sign there. Okay, plus 225. Okay, looks okay. We'll know in a minute. 830. So that's 830 sitting here. And then we're going to take 830 minus 80. 830 minus 80. 750. So remember when we did our other calculation, we got 750. Then we divided by 4, took the square root. So S is the square root 750 over 4, which is what we had last time. So we know what that is. I've got it written down here. It was 13,693. So that has to do with summing these and these, getting the tallies, and then putting them in the formula. And so the only place you might end up with round off might be here when you divide by some number, but that's a whole number, so it's not a big division. And pretty much by hand you get the exact right answer this way, except you have to take a square root at some point. And so that there's a by hand way to do that too, but they don't teach that anymore because it's too hard to do. and the calculators do a much better job. We still teach long division, I think, but we don't teach long square rooting, where you group the digits in the number 2 at a time and you do some stuff to them to get the square root. Haven't done it in ages, probably won't do it now. So there's another method of computing the standard deviation using the sum of the x's, the sum of the x squareds. One of the reasons for looking at these different kinds of formulas is so we get some familiarity with the order of operations and what those things stand for. And so it's not just a mystery of sea of symbols. So if we start messing around with them and putting things in their place, and you base them on sums of columns, you understand what these sums stand for, and it starts to make more sense to your brain. Your brain doesn't want to absorb sigmas for some reason. It just sees them as things that are eating things. But after a while, you just get used to the sigma standing for sums, and the thing in summing will be the guys in here, and these subscripts are slightly annoying, but they just represent the possible different values as I changes, 1, 2, 3, 4, 5, like we looked at before. So that ends sample standard deviation. Then we move over to population standard deviation. So really it's more or less the same formula, but not exactly. So now we compute the population mean. That just means that we compute the mean for all the values. So it's 1 over n, the sum of the x's, like that. We would do that for the sample mean, except then we'd have the sample size here and all the sample values. Now we've got all the values and the population size there. And then in front, we're dividing by n. With the sample standard deviation, we divide by n minus 1. And that's mostly because we don't have all the values, and so that's a compensating measure. What happens here is a little bit complicated to describe, but to get something that represents this in a statistic, the right thing to divide by, it turns out, for this type of thing is n minus 1 and not n, so you get something close to this number, as opposed to if you divide it by n, you get something a little bit too small, it turns out. So this is the population size sitting here. And then if we wanted the population variance, we would just square that. Okay. Here's our example of a population standard deviation. I've got 100 tokens, and 25 are marked with a 1, and 75 are marked with a 0. So that's my whole population. 100 tokens, 25 ones, 75 zeros. The population mean will be the sum of all the values divided by 100. I've got 25 ones and 75 zeros. So when I add them, I'm adding 25 ones to 75 zeros, so I get 25. And the 25 then divided by 100 is 1/4. It is. And then I want to compute the population standard deviation. I'm using the formula 1 over n will be 1 over 100. Now, I've got to remember what the mean is here. So the mean is 1/4. And these numbers here are 0 or 1, depending. So maybe I shouldn't write it like that because it's a little bit messy. I'll just say, okay, if the x's are 1s, now I'm making a bigger mess. If the x's are 1s, I get 1 minus 1/4. That's 3/4 for the 1s. And 3/4 squared is 9/16. So I'm going to get 9/16 here 25 times because there's 25 ones. So I'll get 25 times 9/16, and that's from the ones. And then I'll get the contribution from the zeros. You'd think the zeros don't contribute anything, but they do, because 0 minus 1/4 is 1/4. And we square 0 minus 1/4 is minus 1/4. And you square that, you get 1/16. And I get 75 1/16. Okay. So that's making sense. And then my sheet says that comes out to be 3/16. So I'm trying to figure out why. I can see this 16 down here as the denominator. So I get 75. 25 times 9 is 225. We're going to add 75 to that. It's 300. So I get 300 looks like this. 300 over 100, put it here, square root 300 over 100 times 1 over 16, when I do all that work. And that's 3/16. Okay, so that was right. Okay, and then if you put that on a calculator, we get 0.4330. And as usual, or we had one other time a variance calculation. The variance is the square of the standard deviation. So it's this number under the square root sign. You took the square root, you get that. When you square it, you're going to get this back. So that's going to be 3/16. Okay, so what do we accomplish here? We came up with, found another formula for sample standard deviation. We noticed that the reason for using that kind of formula is because it's based on using sums of values and squares. There's other formulas like this for other computed statistics later in the class. We will probably use our calculator at those junctures, though. But we did this one just to see how the formula plays out. We had the sums of 830 and 20. You put 20 there, you put 830 there, you're dividing by 5. First you square it, so you get 400. Combine these two by subtraction, and then divide by 4 because there's 5 values, and then take the square root, get the same old answer. And then over here, in a population case, the difference between the population case and the sample case is you're saying, I've got all the values, I've measured the entire population, I want to know the standard deviation of those values. Turns out the formula looks like 1 over n here, times the sum of the deviations from the actual mean. In the sample standard deviation case, we had the sample mean there, and the sample mean actually tends to be closer to the values than the population mean would be. And so that's the reason for dividing by n minus 1 instead of n. If that makes any sense, congratulations. If it doesn't, don't worry, we just use n here. In populations, we use n minus 1 for samples. Then we had this example, 100 tokens, 25 ones, 75 zeros, and we cranked out the answer. And we got the variance was 3/16, and the standard deviation was square root of 3/16. And that ends this slide. Woohoo! Here we go.